Welcome back to Employability Improvement Training. I am Ramachandran. I am from Buffalo Industrial Technology Research Institute. In the last video, we saw the contents of this training course and said that in the next class we will see an introduction to the microprocessors. We all know that in the modern computers, everything is represented in zeros and ones. The basis for this is binary numbers. The modern binary numbers was discovered by Leibniz in 1679. Even before he invented binary numbers, it existed in the ancient world. In China, a divination method called I Ching existed in 9th century BC. It had yin and yang, essentially a binary representation. In India, in 2nd AD, a mathematician called Pingala, in his work called Chanda Sastra, has described a method to represent matrices in binary representation. Bushmen of Africa were using a binary system for communication using drums. In binary number system, there are two symbols, 0 and 1, similar to symbols 0 to 9 in decimal system. As in decimal system, binary system also support arithmetic operations like addition, multiplication, subtraction and division. For example, adding 1 and 1 in binary results in 1 0 in binary. Similarly, multiplying 1 1 with 1 1 results in 1 0 0 1 in binary. A binary number can be converted into decimal number by multiplying the value of digits with 2 power n minus 1, where n is its position from right to left. For example, when you convert 1 1 in binary to decimal, we multiply the 1 in 1's place with 2 power 0 and 1 in 2's place with 2 power n, and we get 3, which is the decimal equivalent of 1 1 in binary. We can convert a decimal number into binary by repeatedly dividing it by 2 and taking the remainders in reverse order. This binary number system forms the basis of processing numbers in modern computers. In 1605, Francis Bacon discussed a system where he showed that the letters of alphabet can be encoded in sequence of binary digits. From this evolved encodings like ASCII, Unicode, which represent alphabets of languages, punctuation marks and other symbols. This forms the basis for processing words, language in modern computers in binary form. In 1854, a mathematician called George Boole described a system of logic in his book The Laws of Thought. In this system, variables can have values of two symbols, true or false, usually represented by 1 or 0. And this system had operations like conjunction, disjunction and negation, similar to arithmetic operations in decimal system. From this evolved Boolean algebra. In 1937, Claude Shannon and implemented Boolean algebra and binary arithmetic using electronic relays and switches. He showed that circuits can be constructed using any basic element that has two states. They can be switches, which can be in either on state or off state. Circuit components that represent Boolean logic are called logic gates. Logic gates can be implemented using electronic switches as shown by Shannon earlier. Logic circuits are used to perform all the internal operations of a modern computer. There are three basic logic gates from which all other gates can be done. They are AND, OR and NOT gates. An AND gate is represented like this pictorially. Both inputs must be true for an output to be true. AND gate is used in addition and decision making. The truth table for AND gate looks like this. Both inputs must be true for the output to be true. In all other cases, the output is 0 or false. Next is OR gate. OR gate is represented pictorially like this. For OR gate, both inputs must be false for the output to be false. OR is used in decision making. Both AND and OR can be used in bit masking. Bit masking is used in computer programming to pick individual bits out of a byte or to set a particular bit in a byte. OR is used to set bits to 1, AND is used to set bits to 0, AND is used to test if bits are 1, OR is used to test bits are 0. The truth table for OR gate looks like this. Both inputs should be false for the output to be false. In rest of the cases, the output is true. The third of the basic gate is NOT gate. NOT gate has a single input and single output. NOT is used to invert bits to true or false values. When the input is true, the output is false. Input is false, the output is true. NAND gate is really an AND followed by NOT. Hence its truth table is inverse of an AND gate. When both inputs are 1, the output is 0. The rest of the time, the output is true. NOR gate is really an OR followed by a NOT. Hence its truth table is an inverse of the truth table of OR gate. When both inputs are false, the output is true. In rest of the cases, the output is false. XOR gate detects if the inputs are equal or not. When both inputs are equal, the output is false. In rest of the cases, the output is true. XOR is combined with AND for use in addition. From the basic gates, we can derive more complex circuits using Boolean algebra. One such is half adder. Half adder adds two inputs. It has an XOR and AND gate. An XOR gate represents the sum and the AND gate represents the carry. The truth table for half adders looks like this. When the inputs are both 0, the sum is 0, the carry is 0. When both inputs are 1, the sum is 0 and the carry is 1. A full adder is a circuit which has 3 inputs and it has 2 inputs and the carry from the previous addition. The truth table for full adder looks like this. When all the inputs are 0, that is both the inputs A and B are 0 and the carry from the previous addition is 0, the sum is 0, the carry out is also 0. When all the inputs both A and B and the carry in are 1, the outputs sum as well as carry out are 1. So using logic gates and Boolean algebra, complex circuitry can be built. This is another important milestone in the development of digital computers. In the field of electronics, in 1904, John Fleming, an English physicist, while working on Edison effect, invented vacuum tubes. He found that when a cathode heated starts emitting electrodes, and when another electrode called anode is placed in the tube, it starts collecting electrons. But he found that the current doesn't flow in the reverse direction because anode is not heated, hence cannot emit electrons. This tube came to be known as diode and was used as a rectifier. In 1907, Lee D. Forrest invented triodes. He added another electrode in between cathode and anode in a diode and found that a small change in the grid circuit on the cathode side resulted in a big change in the anode side of the circuit. He named it as triode, and triodes were used for amplification. With the advancement of semiconductors in 1947, William Shockley and his team, they built the first transistor. In 1959, first integrated circuit was built by Bob Noyce at Fairchild Semiconductors. He showed that multiple number of transistors can be built on a single chip. From this large-scale integration, very large-scale integration, integrated circuits evolved. In 1936, Alan Turing invented Turing machine and formed the basis for theoretical computer science. A Turing machine is a hypothetical device which had a tape which contained symbols and a head that can read or write symbols on the tape and move on the tape. It also had a state register to store the state of the Turing machine and an action table that gives instructions based on the state of the Turing machine. His invention formed the basis of theoretical computer science, and all modern computers can be considered as a form of Turing machine. In 1940s, computers were mostly fixed form computers. They were called program control computers. One such computer is ENIAC, which was built using vacuum tubes and occupied a whole room. To program the computer, one has to actually rewire the computer, and to do something else they have to do that wiring all again. A new model of stored program digital computer that keeps its programmed instructions and data in memory was proposed. In 1945, the mathematician and early computer scientist John von Neumann and others described a computer architecture which was based on stored program digital computer model. In 1969, Busicom, a Japanese company, went to Intel for building a processor for a calculator, which is essentially a program controlled computer. Engineers in Intel suggested to them the stored program digital computer model and built first commercial microprocessor. They introduced Intel Microprocessor 4004 in 1971. It had 2300 transistors and it was as powerful as ENIAC. It was built on a single chip, whereas ENIAC occupied a whole room. Then other companies like Zilog, Motorola, IBM, SPARC, AMD all started manufacturing microprocessors at various times. In 1975, Moore, one of the founder of Intel, predicted that in every 24 months the number of transistors in the processors will double. The microprocessors have evolved almost according to Moore's law till now. The inventions we have seen in the previous slides in the fields of mathematics, electronics, material sciences and in computer science form the basis for the modern computers. We will see about microprocessor architecture, instruction set architecture and microarchitecture in the next class. Thank you.